So let's start with the next part of the theoretical lectures on a posteriori error analysis. And this part will require a little bit of work to actually prove everything. And I'll try to do everything with a slow pace. And this lecture will be slightly shorter with respect to the others, if I manage to keep it that way in a certain sense. Okay, so what's the part that we have seen so far? So let me show you two images. These two images are images that are images for bubble functions, and these are going to be two characters that appear in the proofs for the optimality of the a-posteriori error estimations. Okay, so these are bubble functions defined on cells. This guy over here is a bubble function defined on a cell, or defined on a face. And in some sense, the reason why we need these types of bubble functions is that we want to be able to localize the a-posteriori error estimates on some parts of the domain, but without relying on the fact that we cannot integrate by parts locally without having jump terms appearing and without propagating the error information outside of this boundary. So the trick is try to figure out whether it's possible to use as test functions or to write the a-posteriori error estimations using some tricks that allow you to recover a-posteriori error estimations and scale these a-posteriori error estimations with functions that are actually zero on the boundary of the cell, or if you're thinking about the terms that live on the faces that are zero on the boundary of the face, like in these 2 points over here, and that are non-zero just on a compact support around the face, just on the elements around the face. And these are two objects that are going to be used, and we'll call them BK and BF for the proof of the optimality. Okay, so let me recall what we did in the last lecture. And in the last lecture, we started by, I defined the jump of a quantity across an edge. And the jump of a quantity across the edge to be defined was basically using just the first introduction that I had here. And I specified every time that the face was an interior face. And what I'm using today is just a shorthand notation, which is a little bit simpler to use, and that allows also to keep track of, for example, Neumann boundary conditions. And in this particular case, we have that we define the jump of a function a as a vector variable if a is a scalar, or a scalar variable if a is a vector. And it's a plus n plus a minus n minus. And we had the picture showing this type of thing in the last lecture. And the picture was showing something like two faces. This was t plus, and we had here t minus, and outward normal, this is n minus, this is outward normal, this is n plus. And in between these two guys, we assume that there is a common face, which we call f in this particular case. And here we're looking at the jump on f, and we define this jump as something which is independent on the orientation of the things, but only depends on the values that are defined on the two sides, on t plus and on t minus. Okay. With this definition, this is also valid for all boundary terms. And for the boundary which are Neumann boundary, this is going to be the difference between the term an and something which is defined on the boundary. And if you are on the boundary with the Dirichlet part of the boundary, then this term is going to be just equal to 0 by definition. So we set this equal to 0 on the Dirichlet part of the boundaries, and we set this equal to that. And with this notation out of the way, what we had defined was a local error estimator. And the local error estimator that we defined, we gave it a name EK or eta k according to the notations, or ET. So let me just use eta t in this particular lecture today. And eta t is defined as the HT times the L2 norm of the residual on the cell plus, and here now we don't need to specify whether f is on the boundary or not, plus the sum over all the faces which are on the boundary dt there was a term that is 1/2, and then this was hf to the power 1/2, and this was the jump of the gradient UH. And the definitions that we get above, this jump of the gradient that you see here is a scalar, and it's the jump of the normal derivative across the faces. Okay, and this was 0f. And ideally, what we wanted to show is in the ideal world, what we had was one would like to have the following property. Would like to have that the norm of the error, let me use u minus UH semi-normal 1 omega, this is controlled by the sum over t in the triangulation of eta t square. We'll put the square everywhere. And we would like this to be also valid. So ideally, this is a global estimate, it's global properties. And local properties. So local properties, ideally, we would like to have that t eta t square is controlled by u minus UH 1 t square, and this is controlled by eta t square. So we would like for an error estimator to be reliable and optimal. So this part of the inequality is called reliability. And this part of the inequality is called optimality. So ideally, we would like these two properties to hold both globally and locally. And in general, this is false. I mean, if you can do that, if you can prove that, you have the holy grail. So you have found the optimal a posteriori error estimator, and you have found the optimal results for the global error estimators. And let's try to understand why this is false in general. And the reason why this is false in general is because you're usually able to control this guy over here with an h-1 norm of the residual, and not with an h1, not with a residual which is a positive norm of the residual. And the h-1 norm of the residual is usually a non-local norm. So this is something that does not allow you to have a local estimate of these types of error. So one can actually show, and I can actually prove, a global property like that very easily, and a almost local property like this very easily. And today we are going to prove a result which is close to the optimality plus a perturbation, which depends on a perturbation of the right-hand side. In particular, the theorem that we would like to prove today is the following, and is the theorem local optimality. And the local optimality theorem, I'll introduce some notations in a few seconds that will allow you to understand what is the point here. Okay, so what we can prove is actually that eta t, which is defined as ht norm of f minus Laplacian of UH plus sum over t, sum over faces on t of 1/2 hf to the power 1/2 norm of the gradient of UH 0f is actually controlled by a norm of the error, however, not on T, but on what I would call dt for the moment, plus a term that is a higher order, it's a oscillation term on the forcing term. And this oscillation terms is the infimum on VH, on capital VH of F minus VH 0 dt. Okay, so it's not exactly this on T, but it's almost like this on T. So what I'm saying is that if you look at the local error estimator, the local error estimator is not controlled by the error just on T, but it's controlled by the error on something which is surrounding T, plus a higher order perturbation on the forcing term that you have. So if the forcing term in particular, if this term is equal to 0 for some reasons, for example, because the forcing term lives in the space VH, it's a polynomial which is piecewise in the space VH, then this term is not here. And in general, what you have here is that you can actually prove, you can actually show that this term is of high order with respect to the error that you have, here, provided that you can approximate F correctly around the object. Okay, this is the best that we can get. And it's the theorem that we're going to prove today. So the problem with this theorem is that it requires a lot of ingredients, and it requires a lot of little details to be fixed. Okay, and let's start by defining what are the ingredients that are required for this. And in the other direction, we also proved something which was the local version of reliability. So we had a local reliability, and the local reliability was constructed. Sorry, the global reliability was constructed starting from delta T, and delta T was a different notions with respect to this. I will discuss the differences between these two things. So let's take a look at what are the entries in the element that I'm saying here. So let me first start with copy pasting here an image on which I can play around with this a little bit and define what are these two guys. Okay, so I should have here a mesh image, and I would like to define two objects, which are dt and df. Okay, so dt, let me write first what dt is, and then I'll, how do I move that? Down here. Okay, so find first dt is the union of all elements Tn and the closure of that of Tn such that Tm intersected T, closures of this guy is equal F, different from empty set, where dim F is equal to D minus 1. Okay. So basically, these are all elements that share a face with T. Okay. And similarly, I will define df union on Tm of the closure of Tm and take the interior part such that Tm1 intersected Tm2 closure is exactly equal to F. Okay. So two elements are df and dt, And if I take a picture of these two guys, I'll take a picture, for example, this is F here. Then the object that I'm looking at as df is this guy. So this is the simple one. So this is df, and that's f. And instead, for the case of a triangle, for example, let's take this triangle. All the set of elements that share a face with this triangle is called, this is T. And then I have that this triangle over here and this triangle over here and this triangle over here, union T, of course, also T is in this set. This is this set dt. And so all triangles that actually share a face with T, or all triangles that share a face that whose intersection of the faces is F. Okay. First ingredients that I want to consider for the next part. Okay. And second ingredient that I need for that is the bubble function. Okay, so what are bubble functions? Let me just make sure I have all the properties which are corrected. Bubble functions on T or on F. Okay, so how do I define a bubble function? So a bubble function, so BT is a bubble function F. Property number one, BT is positive and the maximum of BT is equal to 1 in T, in the closure of T. Second property, BT belongs to H10 of T. Okay. And third property, which is the most important one, that exists a D, which is a subset of T, such that the measure of D is greater than 0, and such that BT restricted on D is greater or equal to 1/2. So it's a bubble function. So 1/2, it could be any other number in reality, but in 1/2 is a typical convention. Okay, and I can construct such bubble functions very easily, and I can show you exactly how to construct these bubble functions. And the pictures that I showed you at the beginning were exactly an example of such a bubble function. And if you have that this bubble function decay, so one example, one way to construct this, for example, for dimension D equal to 1, is to consider, for example, quadratic functions on the interval BT equal 1, and to consider the basis function associated to the support point, which is in the center. That's a polynomial that is 0 on one side, 1 on the center, and 0 on the other side. And if you look at this, there exists a D here. So there exists a finite measure size D for which this guy is actually greater than 1/2. The maximum is equal to 1, and it's 0 on the boundary. So this function is used to basically to cut off what happens on the boundary, but without losing information about what happens inside the boundary. So we are going to be using this for the proof of the theorem. And for the dimension 2, this is a little bit more complicated, because in dimension 2, what we have is the following thing. A quadratic function is not sufficient because it does not have degrees of freedom in the center of the triangle. So we need to use cubic functions. And cubic functions allow you to have, actually, they do have one single degree of freedom on the center, which is aligned here and aligned there, in line with these guys over here. And we consider cubic functions. So this is in P3 of a triangle, while this is P2 of the triangle in 1D of the segment. And let me call it E, edge or segment. Okay. This is P3 of T, this is P2 of E. And in this particular case, this function here is a cubic function, which is 0 on the boundaries and is equal to 1 here. And if you wrote the contour, the level set contour of 1/2, it would look something like this. Okay, so this is the D that is written in the definitions of the bubble function. Okay, so there is a set in which the function is greater than 1/2, and this is used. It's useful for what we need to have afterwards. So if this is the case, so with A, B, and C as properties, there's two inequalities that follow. Then this is a very important lemma that is very important for what we need to do next. Then what we have is that property number 1 is satisfied, and property number 1 is that if you take the norm of BT times C, the L2 norm on T, this is controlled by the L2 norm of phi alone. So there exists a constant such that this is satisfied. And moreover, if you take BT to the power 1/2, you can also control this guy from above. Okay. The way to prove this is actually by transforming things into the reference element, proving everything in the reference element and transforming back. And it's simple to write this in terms, if you prove the square of this. The square of this is trivial to prove. The second property is basically an inverse property. And it says that for any V, which is a polynomial of order K on T, so for any polynomial of order K on T, and K here is greater or equal than 1, if I remember correctly. So for any polynomial with the order greater than 1, what we have here is that there is a inverse inequality that can be written directly. And let me write the inverse inequality first. And the inverse inequality is the following. So you can control BT phi, the one semi-norm on T, by paying H minus 1 with the norm of phi 0 T. Okay, so you control the H1 semi-norm when you scale the function phi with BT, provided that you pay with HT to with HT inverse and the L2 norm of 0T. And you control the L2 norm of the scaled version with BT, both from below and from above, provided that you pay a power 1/2 when you look at it from above. Okay. So the same thing will apply for faces. However, for faces, we need to do something a little bit more intricate. So you can apply this for T. So all these two inequalities are valid for T in RD simplex. Simplex or hyper cube slash, well, hypercube means quadrilateral hexahedra or segments. Okay. So this is an example of bubble functions. It's these finite things, and of course this is the simplest case for simplices. Yeah, for simplices, it's very simple to write, and for quadrilaterals, it's even simpler. So the pictures that I showed you at the beginning, which is this one, shows you an example of how this works, where the level set of 1/2 is roughly this guy over here. And the same is valid for this object, and I'll talk about this object right away. Okay, so of course, if I want to have a bubble function that is a bubble function on the face and also a bubble function on a object with a larger support, I cannot use a single element, but I have to use two elements that share the same face. And when I use the two elements that share the same face, then the actual things that we're going to be needing are the lifting operator, and then we are going to be using bubble functions on the lifting operator. Okay. So let's define what is the lifting operator. And this is usually called RE, and it goes from F into values df. Okay. So actually, sorry, I wrote it as F with values in df. The lifting operator does not go from F, but it goes from a P. So it goes from pk of F to pk of the F element-wise. Okay, so let me be clear about how this works. Okay, so what's the lifting operator? We call this RE. So in the literature, sometimes it's called also capital PF, but I don't want to make this. I don't want to confuse you with the notions about polynomials and the lifting operator. So the lifting operator is an object that does the following thing. In the proof of what we want of the optimality, what we're going to be needing is we're going to be needing to put into relationship something that happens on the face with something that happens on the side, on the actual surrounding elements. Okay, this is F here, this is T1, and this is T2. Okay, and we assume this is the face that we have over here, and we assume that both T1 is equal to F1 of T hat, and T2 is equal to F2 of T hat. Okay, both T hat are the same, so we have basically the reference element we've called T hat in all the previous lectures, so I'll keep using it in this way. So this is T hat, there's a point X hat here. And with this, I have one object goes into T1, which is called F1, and one object that goes into T2, which is called F2. And now, what I want to do is I want to lift the value of a function which is defined on the face F inside the entire set df in such a way that you have good properties of conservations of norms in L2 with respect to the various objects. And in particular, we would like to have the following things. If let's say assume that F hat is such that F1 of F hat is equal to F2 of F hat and is equal to capital F. Okay, so what I'm saying is that F hat is mapped to F, both for F1, for T1, and for T2. Okay, and assume that F hat is aligned with X1 hat. This is an assumption, is a simplifying assumption. But not necessary, okay? It simply simplifies the way to write things, but it's not necessary. So you might have different faces aligned. You might have the different faces are the ones that are actually transformed in there. But by rotations, you can always point this to the case that I'm writing now. Okay, so there's always a possibility to write this in such a way that this is the case. This is true. Then what I want to say here is that the lifting of a function v evaluates that the point x is defined as, well, so what's the operation that I want to do? I take any point which is in here. So I take this is x, and from x, I go to x hat through f1 to the minus 1. So this is f minus 1 of x. When I arrive here, I project this point onto f hat. Okay, so that means I take E1 scalar product with that. And let me write this simply as pi hat of f hat, which is an orthogonal projection of this guy. I'll write what it is in a second. So pi hat of f hat with inverse of x, and then I go back, oops. I go back with this point that is over here to the corresponding point on the face. So this becomes f1 of that guy, and I evaluate the function v, which is defined only on the face. Okay, so if you write this with the classical notation, this is v after f1, after pi hat over f hat, after f1 to the minus 1. And this is when I restrict this to T1, and of course, T1 or T2, this is F1 or F2, F1 or F2, and pi hat, F hat, is defined as E1 dyadic E1, which means if I take a point x hat, this is simply the first coordinate of the point x hat. Okay. It's the orthogonal projection of x onto f, of x hat onto f hat. Okay. Okay, if I try to look at this, and of course this is, if you haven't seen this before, it's a little bit daunting. So let's try to take a look at the picture of this guy, and let's try to take a look at the contour plots of what this picture would look like for a particular case. So if you look at the function here, then this function, so for example, so this face here is like that. It's just a function which is the same along all these lines. And the values of these functions depend on the value on the face, and the same is valid on the other side. So this is an example of the lifting operator of a function B. So these are contour plots. Of RE of V for V in P1 of F. Okay. So what I said here in reality can be applied to any function, which is a C0 function of the face, or for any h1 function of the face, you could do this as well, but we're not going to be too picky about for what function this is defined. So for the moment, since I'm going to use this only for polynomials, then this is going to be a polynomial of the same order of the polynomials on the face along the f element-wise, meaning that it's the same polynomial that is written on the face, but I replicate basically parallel to this face inside the triangle here and inside the triangle there. Okay? Okay. Now, given this, I define a bubble function on f and on the f. So the bubble function on f and on the f, that means that it is a bubble function for both f as d-1 manifold and for f as d manifold. So in other words, I want to have the properties that BF is between 0 and 1 for both cases. I want to have the property that B is H10 of F when restricted to F, and BF restricted to F is H10 of F, and BF is also H10 of the F. Okay. In other words, I want the bubble functions to be a function that is 0 on the boundary of the F, and is 0 on these 2 points, of course, because it's 0 on the entire boundary. And it's a function which is between 0 and 1. Okay. Second property, if I have in this case, there has to exist df, which is a subset of f, such that the measure of df is greater than 0, and this is a measure of dimension d-1, where bf is greater or equal than 1/2. So bf on df is greater. Oh, sorry, I should have not have called it df. Let me call this as d tilde f. D tilde f, and this is d tilde f. And d, there exists a d tilde df included in df, such that the d tilde of df has measure which is positive, and this is a measure of dim measure of dimension d, where bf on d tilde of df is greater or equal than 1/2. Okay, so these are the properties of being a bubble function for both phase and df. And if you have this, then the following 2 things are also true. And let me, of course, we have the same thing that is true for the for the bubble function alone, but we want to have this with the lifting operator involved. So we have two properties, actually three properties, but two of them can be, one of them can be derived from the other one. So the main property that we have here is that if you take BF of a function phi 0f, this is controlled by the norm of phi on the face f. And again, this is the same as before. This is BF to the power 1/2 0f, and this is for any phi in pk of f. Okay, so this is for any polynomial functions. Okay, and the second property now makes the appearance, makes the lifting operator appear. Right, so we have it's basically similar to the inverse inequality that we had before. Let me put the hf to the power 1/2 here first. So this is the norm of phi on the face. This is controlled by the norm of BF lifting operator of phi, and now this is on df. Careful. And again, we have hf to the power 1/2 of phi 0f. And this is the important part. So this is very important. What we want to do here is if you multiply, pre and post multiply by a bubble function, then you can control the L2 norm on the face by scaling with hf to the power 1/2 with the lifting of that function. And the lifting of that function is simply basically the replication of the function across the phi, and then hf to the power 1/2 on the norm phi on 0f. And the last property, it's a consequence of the first and second property and of the fact that the bubble function is a bubble function on the face, but allows you to basically write the inverse inequality of the bubble function with respect to the lifting operator of phi. This is on 1 df, and this guy here this time is hf to the power -1/2, and then the norm phi 0f. Okay, so I know this is a lot to take, but keep in mind these are very useful properties to have in your bag of tricks when you want to prove error estimates and a posteriori convergence analysis on finite elements. Okay, so let me move this slightly better centered. Okay, questions so far? Possible construction of S. Now I take, instead of taking cubic functions, I take quadratic functions, and I take two basically quadratic functions on two neighboring elements. Take these guys over here, take these guys over here, there's these guys over here. So these are all the support points for quadratic functions on triangles. And here I take the basis function associated with the node, which is on the center of the face. And this will be d tilde f. And this will be the segment d tilde f. And here we have df. Okay. Okay. So this guy over here is the possible BF basis function of P2 of T associated with center of F. Okay, does that make sense? So this function satisfies all these properties. Okay, so why do we want to use, I mean, this is a long introduction in order to be able to get to proof of what we want to show. And what we want to show is local optimality, which is this guy over here. Okay? So we would like to show that eta t is lower or equal than that guy. So let's start by copy pasting this. And now we prove this. We have all the instruments to prove this. Okay, so we start by taking a look at eta t squared and actually taking a look at the various ingredients of eta t. So we said eta t contains two parts. So one part, which is part number one, is ht, and then we have the norm of f plus Laplacian of uh 0 t, and then we have the sum over all faces that belong to the boundary of t of 1/2 hf to the power 1/2 norm of the jump of the gradient of h, and this is on the face f. Okay. So this is what we want to estimate and to prove that is equivalent to what's written on top of that. Okay, so let's start by giving numbers and names. So this is part number one, and this is part number two. So we start with part number one, and we observe first of all that if I take f plus Laplacian uh 0 t squared, I can use triangle inequality to actually show that for any arbitrary v, so f minus vh plus norm of vh plus Laplacian of uh 0 t, this is valid. Okay, and I'm simply using triangle inequality for this. Okay. Oh, actually, sorry. Without the squares, if I want to use triangle inequality. Okay, so let's start by estimating term number 3, because this term over here, in some sense, it's already part of what's written on top here, right? Okay, so let's estimate term number 3. So this is on 0 t, and this is again on 0 t. So part number 3. For the part number 3, I take the square of that. And now I would like to use the fact that this can be scaled. So what I want to do is I want to localize this and try to apply integration by parts until I get something which is useful for what we want to have. Okay. So in order to do that, what I do is I basically use the first inequality that we wrote above, by saying that this is more or equal than bt times vh plus Laplacian of uh 0 t, and there's 1/2 in front of this guy with a square there. Okay, and this is the first inequality that I proved. I mean, I didn't prove it, but I told you how to prove. But it's trivial equality to show with passage to the reference element to back and forth, and it comes from the fact that bt is a bubble function. Okay, so I'm localizing this in order to be able to integrate by parts and get rid of all the terms that are on the boundary. So if I now write this explicitly, this is exactly like writing the integral over t of vh plus the Laplacian of uh bt vh plus Laplacian of UH in dt. Okay, so this is exactly what I've just written. Okay, and now the principle is I would like now to be able to, in some sense, to put this into relationship with the norm that we already have, so with the terms that we want to show, and in particular, we need f and u to appear in this equation. So we can use the fact, let me just move this on the right, that we can add and subtract 0 to this term, to these objects. So what we do is we subtract f and the Laplacian of u, because this term over here, since Laplacian of u is equal to f, minus the Laplacian of u is equal to f, this is exactly equal to 0. Okay? Okay. Now, split the two integrals in the two parts that contain the part that contain vh minus f and the part that contains Laplacian of u minus Laplacian of uh. And I would like to exploit the fact that bt is 0 on the boundary. So bt, if I take on the boundary of dt, is equal to 0 by construction. Okay, so this means that I can take the following. I take the first part and I rewrite it simply as this. And I have bt vh plus Laplacian of uh here. And I take the second part and integrate by parts, exploiting the fact that this is 0 on the boundary by construction. So I get the integral on t, there's no boundary terms. And I have minus Laplacian of u minus gradient of u. Sorry, there's a plus. This is a plus, it's not a minus. Okay. I have minus Laplacian of u plus Laplacian of uh. I integrate by parts and I get gradient of u minus uh. And then on the other side, I get the gradient of everything that is left over there. This is bt times bh plus Laplacian, Laplacian of uh in dt. And now I observe the following thing. I can use Schwarz inequality in all of the terms I have here. So I can Schwarz this together with that, and I can Schwarz this together with that. And here I exploit the fact that this object is a polynomial times a bubble function. And I exploit the fact that this is exactly the error that I'm looking for. All right, so if I look at these two terms, what I obtain here is this is the norm of vh minus f 0t. I exploit again the inequality that I had above. So this would be the L2 norm of bt vh plus Laplacian of uh. And I know that from the left, this is equivalent to the norm of vh plus Laplacian of uh alone. So this would be bt vh plus Laplacian of uh 0t. And now I would like to exploit the fact that this is smaller or equal than the norm of vh plus Laplacian of uh 0t. And on the other side, I do the same. So on the other side, what I get is semi-norm u minus uh 1. And again, here I write the semi-norm. So it's the L2 norm of the gradient, which is the semi-norm 1. And here I have the L2 norm of the gradients again, bt vh plus Laplacian of uh 1. And again, I can exploit now the fact that this guy over here with bt and the one semi-norm satisfies an inverse inequality, which is ht to the minus 1, semi-norm, norm vh plus Laplacian of uh 0t. Okay, and of course I can do this because vh plus the Laplacian of uh is a polynomial. Okay, then if I keep going in this case, what I would obtain here is that all of this is smaller or equal than VH plus the Laplacian of UH, 0t, which multiplies U minus UH 1 with ht to the minus 1 plus the norm of VH minus F. And so far, VH is arbitrary. And of course, if I read what's written on the left of this inequality, I have exactly this guy square. Okay, so this guy square is smaller or equal than itself times something, which tells me that at least the first term is controlled. So this implies that number one, I can control HT, norm of VH plus Laplacian of UH, 0t. This is controlled by, locally, by U minus UH plus HT, norm of VH minus F, and both of this guy are just on T. So far, I have not needed anything else. Okay? So the first term is controlled, and this is exactly what we needed. If you look at the inequality that we have over here, the first part is controlled by one term and one term, and I have exactly this here, taking the infimum over V, and this is for any VH in capital VH. So this is valid for any VH, okay? And of course, the reason why this is valid is because I've already proven that this can be written as the sum of two parts. One part, which is here, F minus VH, 0t, plus another part, which is here, which is VH plus Laplacian of UH. So this gets incorporated into this, and the rest remains outside, okay? So this means if I multiply HT times U, so this was F minus plus Laplacian of UH is controlled by HT F minus VH, which is what is written there, plus U minus UH 1t. Okay? And the difference between these two inequalities is simply the fact that here I have F plus Laplacian of UH, and here I have VH plus Laplacian of UH. And this part is the second term of the triangle inequality that I've written here. Okay? So F plus Laplacian of UH is equal to F minus VH plus Laplacian of UH, and this part is equal to that plus another part. If I multiply everything by HT, I get what I want here. Now, the second part, it's the inequality with respect to the phase terms. So let's start by considering just this term for the second, for a moment. So I copy that, and I try to estimate this. So this part over here is, I look at this as the square of this part. And now, what I want to say is that this is smaller or equal the same thing that we did before, but instead of using BT, we use BF. So with the boundary phase bubble of the jump of the gradients of UH. And of course, this is BF to the 1/2, sorry, otherwise this doesn't work. And I have the square there, and now I keep going in this direction, and I try to do the same thing that I did before, and I go from the faces to the rest of the cells. So here, what I have is that this can be written as the gradient, the jump gradient of UH times BF times the jump of the gradient of UH, and integrated over the faces. And again, here, I want to add something which is 0. And in order to add something which is 0, I consider the fact that the jump of U does not have a jump of the gradient across the faces, across the interior faces, because it's an object that has the Laplacian of U is equal to 0. So I can have that this part over here, this is equal to 0. So I can add it and subtract 0, and nothing changes. Okay, so I add 0 here. And now I try to basically do the same things that we did before. And however, I want to move this into the domain, and I want to get rid, and I want to basically to make the force terms up here instead of the gradient of U. So I would like to integrate by parts again and obtain that. So in order to integrate by parts, what I'm going to use is the following. So if you have two arbitrary functions U on df u v, this is equal, of minus the Laplacian of u v. We know that this, by integration by parts, is equal to the integral of df of grad u grad v minus the integral on the boundary of df of Laplacian of u, and grad u dot v. And this is for any functions for which this actually makes sense. And if you want to make sure that this actually makes sense when you have jumps on the gradients, then you have to make sure that this is done on the sum of the triangles that belong to df. So this has to be done piecewise for this to make sense. So let me write this as something which is piecewise. This is for t in df of the integral over t of that guy. And I'm summing this guy over here. So this is on the boundary of t. Okay. And now what I want to show here is that if I look at this integral over df of the minus the Laplacian of u v, this is for any v in capital VH. I'm not doing anything in particular here. I'm simply just integrating by parts these two guys. Then this guy over here, which is written on the right, is going to be written as the integral of the on df, on the full df of gradient of u gradient of v, plus the integral on the face, actually minus the integral on the face of the jump of the gradient of u times v, minus the integral on the boundary of df of n gradient of u v. That's for hv in vh. Okay. So if I want to look at this guy over here, if I have that if v on the boundary of df is equal to 0, I don't need to have this on vh. So this is for any v. So what I wrote here is valid for any v which is h1 piecewise, for any v smooth enough. Let's write this for any v smooth enough. Okay. So when I say for any v smooth enough here, what I mean is that all the integrals that appear here make sense. Okay, so it makes sense to take the Laplacian of u multiplied by v on integrated over the f. So v has to be globally, if the Laplacian of u is in L2, v has to be in L2. The gradient of v has to be in L2. So this makes sense if the gradient of v is in L2 piecewise. So everything is fine. And here, this makes sense, provided that it makes sense to integrate on the face f the scalar product between these two guys. So this can be in h minus 1/2, and this can be in h1/2, and everything still makes sense. Okay, so if v in the h is equal to 0, then what we get from this is simply that you can rewrite the integral over f of the jump of the gradient of u, and this is of course for any vu is moving enough. Okay, so both these are for arbitrary functions for which everything here makes sense. Then I have that the integral of the gradient of u times v is exactly equal. So I won't have this term if that part is on the boundary is equal to 0. So if you get that is equal to 0 there, then what we need, what you're left over here is just minus Laplacian of uv plus the integral over the f. I think I have to be careful with the signs. This is the Laplacian of uv with the signs because there's a minus sign in front of here. So this is the same sign that has to be there. And I think this is, all of these are with the positive sign. So they should be gradient of u, gradient of v on the f. Okay. And now I want to apply this to what? Well, I want to be able to do this for, and of course here, I can take the Laplacian of u or the Laplacian of v and everything would make sense. But here, we want to maintain the the usefulness for this is if I apply this to these objects in one side and to these objects on the other side. So let's try to understand what's the most convenient way to apply this. So if I take the Laplacian of u multiplied by bf gradient of vh, okay? So the Laplacian of u bf gradient of vh is then something that I can use here. Apply this to gradient of u bf gradient of vh, and this is on the integral of the face. So I'm taking that object to be this guy over here, and I'm taking basically the gradient of this guy, bf times the gradient of uh to be the lifting operator. So I want to apply this lifting operator. Okay. So here, this should become, starting from here, I just copy over what we had here. Not to keep going up and back and down, then this becomes smaller or equal than the integral on f gradient of sorry, so this would be the, I apply this there, I have the jump that is present here becomes Laplacian of u on each one of the two entries plus gradient of u, gradient of v. Then this should become, if I wrote it in this way, this would be the sum over t in df of the integral over df of what? This be the Laplacian of uh minus Laplacian of u applied to BF. And now I take the lifting of the gradient of UH, because I want to move this inside in such a way that I get the correct function inside. Okay. So if I take the lifting of the gradient of UH, this is a function which is equal to the gradient of UH on the boundary, the jump of the gradient of the gradient of UH on the boundary, and I integrate parts this guy by exploiting the fact that here I can just plug in by construction the same lifting operator that I had above, because this is the identity on the face. Okay, simply because of that, because this is exactly equal to the jump of the gradient of UH on F. Okay, so if I apply the lifting and I apply BF re of the jump of the gradient of UH, so this part is the first part, and then the second part I can still write it as the integral on df of the gradient of UH minus the gradient of U applied to the gradient of BF lifting of the gradient of UH. And this is in D, and this is in dt as well. Okay. So here I need to split the integral in two parts, and here I keep the integral separated. Of course, in order for this to be valid, probably I should have written this integral here also split into two parts. So this would have been the sum, the sum over t in df of the Laplacian of uv. Okay, and again here this is the same. This is the sum for t in df of the Laplacian of u t integrated over t. Does that make sense? So I'm splitting things various integrals, and I'm making sure that I'm left over with a part which is on the face. So this is the only thing that survives with respect to the integrals which are outside of the face. And in order to be able to do this, I have to make sure that they make sense of the function u inside the domain. So the reason why I need the lifting operator is precisely for this. I want to transport the jumping gradient of u as a function which is inside the domain. And this is exactly what this object is doing here. And now I want to exploit the properties of the bubble functions that I have shown here, which are the properties that allow me to exploit, using inverse inequalities, things which are defined inside the domain df with things which are defined on the face only. Okay, I want to go back and forth in order to provide an estimate which depends only on the jump of the gradients and on the exact solution u, which is appeared here, and for which now I have various things that I can do. So the first guy is smaller or equal of the sum for t which are in df of what? The first guy, I use Schwarz inequality, and I exploit the fact, sorry, this would be t, otherwise this doesn't make sense. It's the sum for t in df of what? This would be the norm of the Laplacian of uh plus f, because the Laplacian of u is equal to f. This is what I want to have. This is 0t. And now I have, this is bf re jump of the gradient of uh. So I'm doing a lifting with the bubble function in between. And for what we wrote before, this is smaller or equal than hf to the power minus 1/2. And this should be the jump of the gradient of uh 0f. So the first part, from the here, so I'm applying Schwarz inequality, and I'm taking the L2 norm of this guy on T, and the L2 norm of this guy on T should come out from this guy over here. Oh, sorry, I think I put the wrong powers. So the L2 norm of this on df is controlled by the h1/2 norm of phi 0f. Sorry, not h minus 1/2. This is the straight. This is not the inverse inequality. This is the direct inequality. Okay. So we have h1/2 of the gradient of UH here. And now I control the last two terms. And the last two terms is, this is the gradient of UH minus gradient of U semi-norm. This is U minus UH1 on df. So this is normal. This is now enlarging now the support of this guy to the union of the supports of the face of the elements that actually share the current face. And on the other guy, I have the norm of BF and the lifting of the gradient of UH. And this is the one norm df. And once again, I want to exploit the fact that this is smaller or equal than hf to the power of minus 1/2 this time, the norm of the gradient of UH 0f. Okay, so this part over here is smaller or equal than hf to the power minus 1/2. Actually, let me write it below, because otherwise it's not clear what am I referring to. So this this guy over here should be, I don't know what this comes from, and I think comes from here. Okay. Okay, so I'm left with, as before, the jump of the gradient of UH 0f square is controlled by two terms. One is the U minus UH norm 1 df. And the second term is plus the gradient of UH plus f 0t and now I should have a power. So one of the two is multiplied by a power minus 1/2, which is this guy over here. So this is multiplied by power hf minus 1/2, and this is multiplied by a power which is hf to the power 1/2. Which in particular implies that if you multiply, as in the, if you have this in the error estimator you have multiplied by a power hf to the power 1/2, then the first term will have hf to the power 1/2 disappear, and the second term will have a term which is hf to the power 1. So we have here that the square root there disappears because I have to simplify this with the remaining terms, which are these two guys over here and that guy over there. So the square that I have on the left disappears. Okay, and I'm left with the second estimate that I required for that. And the second estimate that is required is that hf to the power 1/2, actually 1/2 hf to the power 1/2 of jump of the gradient of UH 0f, this is what is inside the error estimator, is controlled by U minus UH 1 df, because hf to the power hf disappears. And here I have ht, the Laplacian of UH plus f 0, and this is not t, but it's 0 EF. And here, this is owing to the fact that HF is equal to HT for shape regular triangulations. Okay, so for a shape regular triangulation, what I have is that this guy over here, which is a term that is appearing in EK, controlled by u minus UH on dF and HT times gradient Laplacian of UH plus F in dF. Now, if I put together the two parts, sum 1 and 2, and take the inf on VH, and what we obtain is that eta t is controlled by u minus UH. Now I have to sum over all dF for all faces, and this is exactly the definition of dt. Okay. And on the other side, I have the same thing. So I have something which is now I have to keep going. So Laplacian of UH times F has been already controlled above. So we have the estimate of the Laplacian of UT times dF, which is this term here. Okay, so we have this already controlled, and putting the two estimates together, we get exactly the result of it here, which is infimum for VH in capital VH of F minus VH, and this is 0 dt. Okay, so this is an estimate which is quasi-local, that gives you the optimality condition for the a posteriori error estimator, with an oscillation term, which is here, that depends on the data. So that depends on how well you can approximate the data. You cannot get rid of this, unfortunately. So there's various ways in which you can control this, but one essential part is that in order to be able to integrate exactly the various things that appear, like the error estimator that you have on the left here, you have to make sure that, for example, the number of quadrature points that you use to get rid of this guy over here, to estimate this guy over here, has to be such that the term that the error that you make on F is higher with respect to the error that you make on the approximation error, which is this guy over here. Okay, so if you can manage that, then you're good to go. So the essential part here is to integrate this exactly for all the polynomials that are exact in VH. So if F was exactly in the space capital VH, this should be 0. And if it's not, then this is something which is on the order, which is with the lower order with respect to actual local error, which is what you would like to have. Okay. Good. So this is a long proof, I understand, and it contains a lot of details, but in reality, it's not a difficult proof. It's just a lot of small things that need to be fallen into this correctly for you to understand everything. Right? But this is the main thing. So let me just summarize, and let me just quickly go through the proof again, starting from the definition of the bubble functions, which are used for the localization of the error. So the way that we proceed is by writing the error estimator and writing the square of the error estimator times a bubble function. And we explain the fact that the L2 norm of the error estimators locally on the element or on the faces can be controlled by that same error estimator multiplied by a bubble function, provided that the bubble function has satisfies properties. By exploiting that, when you integrate by parts, you get rid of all the integrals that would appear on the terms on the face of this guy over here, and you're only left with the cell part of the estimator when you take the first part, and the face part of the estimator when you look at the second part. In order to be able to do the second thing, you have to do some tricks, because you're trying to basically estimate something which is defined on the face, which is the jump of the gradient of the discrete solution on the face, and you want to distribute this part on the entire set of cells that share that face. And in order to distribute that in there, we introduce the lifting operator. The lifting operator is an object that actually transforms the function which is defined on the face into a function which is defined on the entire domain that you have over here in a parallel way with respect to the face. So in the particular case, for example, here, this for the curved domain, it would have transformed the face into a function whose contour plot would look like the one that I'm seeing here. And just by replicating whatever was written on the face across all of the other guys. Once you have done that, you make that have 0 boundary values on the boundary by pre-multiplying that with BF, and you use the estimates on the bubble function F. So this is the main idea. So by the definition of the jump, we have the local error estimator, which is defined as the sum of 2 contributions. So this part is the Kelly error estimator that is implemented in the DIL2 library. This is what we added to the Kelly error estimator in order to have also control of the local gradients. Ideally, you would like to prove this from the global and from the local point of view. You can actually prove this quite easily. So the global property from above is easy to write. The global properties from below is also easy to write, because you can actually prove the local optimality. The local properties, this part is not easy to prove, and this part instead is easy to prove, provided that you accept to have an estimate with a perturbation term that depends on the force term, and provided that you don't look just on T, but you look on something which is larger than T. So in general, you cannot prove local properties. This is false in general. What you can prove is a local optimality property that contains a term like that is usually called oscillation term with respect to F. And in the literature, the most often used version of this is actually done with the L2 projection. Well, actually with F minus the local average of F in L2 instead of this. This is a little bit more general and allows you to get better results with respect to what you find in the original paper of Verfurth. So Verfurth papers originally proved this for F minus its average instead of using the actual interpolation properties of F. Okay, and here we have very often the sets dt and the sets df, and by dt and df we mean all the elements that share a face with t. This is not the same as delta t. Delta t was all the elements that actually shared a vertex with t, and so this would include also all of these terms over here as well. So all of this would be included in delta t, while here dt only contains the one that share a face. Okay. Second ingredient, we introduced bubble functions, and we showed an actual construction of bubble functions based on finite elements. And this is general. It doesn't need to be a bubble function in terms, doesn't need to be a polynomial function. It can also be something which is not polynomial. Okay, so it's the properties of this come from the properties of the transformation of the local domain D into reference element and showing that everything works in the reference element. And we use these 2 properties, which are the main properties that we need to have for the bubble functions, which means that pre and post multiply, so pre-multiplying with the bubble function or with the square root of the bubble function allows you to control the L2 norm of the function with the square root of the bubble function, or to control the bubble function times the function with the L2 norm of the function itself. So you have this equivalency here, and you also have an inverse type inequality that holds for scaled function with the bubble functions there. These are very simple to prove and very simple to show. And after you've done that, we have introduced the lifting operator, which was the one that actually transforms the functions on faces, on functions defined on all elements that actually share that face. And once you've done that, you can actually write it explicitly in the way that I wrote here. Well, it's not essential as long as you understand how that works. The application of a bubble function, which is a bubble function both for the face and for the f, then allows you to obtain some properties like the one that you had before. In addition, the properties that allow you to measure sort of inverse inequalities and trace inequalities applied to the bubble functions properties that we had above. So you have norms on the face weighted with hf to the power 1/2 is controlled by the norms of the lifting operator, which is scaled by the bubble function, and this itself is controlled by the norm of the face. It's equivalent to the norm of the face scaled with hf to the power 1/2. Okay, and the inverse inequality is the same as before, with the catch that you have to be careful because this is a codimension 1 object and this is a codimension 0 object, and therefore you have a power which is -1/2 here, which comes from the trace inequality part of the theorem. So the trace inequality would allow you to control the 1 norm using the 1/2 norm on 0f, and you control the 1/2 norm on 0f using the 0 norm on f through the inverse inequalities that may disappear here. Okay, and now after that, you simply apply the definition of the square of each one of these terms over here and do some calculations, adding and subtracting u and f to obtain exactly what you want to obtain. Okay, so this is the principle in which this is used. Let's now go to the last part, which is going to be a little bit discursive, I would say. I don't want to go into too many details, but how do we construct a new mesh? So once you have the error estimator, so constructing a new mesh. So the most important thing to understand is that one would like to have error balancing and we will try to understand why error balancing is a good idea. Okay, so the error balancing would like to be, so given a tolerance, since we know that the global a posteriori error estimation is reliable, so reliability implies that if the sum over k of eta k square to the power 1/2 is more or equal than a tolerance, then u minus uh1 is more or equal than tolerance. Because you can plug u minus on the left of this inequality and you can keep going. Okay, so you can guarantee in a certain sense, let me actually do that. So it's much easier to understand what I'm writing. So what I'm saying here is that the error is controlled by the sum of local error estimators, and if this is satisfied, if sum of k eta k square is more or equal than the tolerance, then u minus is more equal than the tolerance. Okay. So given the tolerance, this allows you to verify whether the global solution that you have accurate solution with respect to a target tolerance. And now, of course, if you want to make the error as balanced as possible, what you would like to have is that the total number of elements, so let me call this mi, is the number of elements of tau I, number of elements of tau I. So this is a grid at refinement level I. Then what we would like to have is that the I+1 grid that I obtain is such that so for each ti in ti+1 in tau I plus 1, eta ti plus 1 is, well, the square of that is controlled by tolerance square divided by I plus 1. Okay. So this is somehow the target that we would like to obtain. And the reason why I would like to obtain this target is because if you obtain this, it's possible to prove that the error that you make at the end of the refinement strategy is the optimal error, in the sense that it goes like the correct power of the number of degrees of freedom. And so let's try to understand, first of all, what is the brain principle in which we can do this. So there's two different approaches. One approach is the one that is used by the library DL2, which is called the bulk chasing algorithm. Or Dörfler algorithm, or fixed fraction algorithm. These are all different names for that. So fixed fraction is the name that is used in the library itself. Okay, so it's a bulk criterion is also another way to call this, bulk criterion. Okay, so the bulk criterion is the criterion. So it's simple. Given theta, which is smaller than 1 and greater than 0, we define E taught is the sum of eta k, the sum on k of eta k I square to the power 1/2. And you mark for refinement, the smallest subset M in tau I, such that the sum for all ki in M of eta ki square to the power 1/2 is, well, actually, greater or equal yes. So basically what you do is you order all the eta k's, and then you keep summing them until you get to a fraction of the total error, and you select the smallest number of elements such that the fraction of the total error is contained in the theta fraction of the total error is contained in the elements that you want to refine, that you marked for refinement. And it's the smallest subset M that satisfies this. So basically, you keep adding elements to refine, you keep marking those elements for refine, you order them. So the steps for the algorithms are the following. So 1, order Ti such that, sorry, this is T Ki such that Ti K, the eta of tki is smaller or equal than eta tk tji if j is greater, equal, or smaller equal. Depends on how you want to order this, okay? So we order them in such a way that whenever you have a smaller j with respect to k, then, or a smaller tk with respect to j, so let's use the same order. This is when k is more or equal than j. Okay, so in this particular case, once you've ordered those, then what you do, you start by 2. You compute E tot. This is for the sum. It's the sum of all the elements that are in the current triangulation of the eta t square by 1/2. And then 3 start with so mark for refinement up to element, let's say k bar. So probably this would have been better to do this in the other way, the other direction. So let's say j smaller equal k. Such that, so what we want to make sure is that the sum of j that goes from 1 to k bar of eta t j square power 1/2 is greater equal to theta E tot. And if you take one less, this is false. So you have tj square 1/2 is smaller than theta E tot. Okay. So what you do basically is you order all the elements. This is the exact algorithm that is done in the library. In the library, this is what happens. You order all the elements in such a way that the error is increasing. If this is what I'm saying here, so I take the element 0 is the one with the largest error, element 1 is the one for the second one, element 2 is the third one, and so on and so forth. And I compute the total error of these guys, and I mark for refinement up to element k star, where k star is the minimum number for which this is satisfied. So if I take k star -1, I get that this is actually smaller than theta E tot for a given theta. And theta is a number which is between 0 and 1. Typically, theta is a number which is around 0.3, 0.1, 0.2, according to the type of problems that you have. This actually works. Okay, and this is called fixed fraction algorithm or bulk chasing algorithm or bulk criterion, and it allows you to basically select for refinement just the number of elements which are contributing the most to the error. Does that make sense? Okay, and now the most important part here is the understanding on why this is useful, right? So if with a quasi-uniform partition, quasi-uniform partition, we know already that, I mean, one thing that one can say is the minimum of HT is similar to the maximum of HT. And it's also similar, minimum for T in tau, for T in tau. And also, all of these are equivalent for a quasi-uniform partition. So there exist constants which depend only on the shape regularity of the triangulation, for which this is the case. So you can always have constants that allow you to find these inequalities, and the constant only depend on the type of shape regularity of the single element. And if you look at it in this way, then in particular, you have that this HT is proportional to basically to well, what you know is that if you take the measure of omega and you look at the number of elements, the number of cells that you have, and you write this as the number of cells, not the number of degrees of freedom in this particular case, but the number of cells, this is proportional to HT to the power D. And this is for uniform triangulations, right? This is what usually happens. So you have M, which is the number of elements. So in other words, you have that HT for uniform partitions is proportional to M to the power -1 over D. Okay? And simply because you're splitting the domain omega in almost uniform grid size, and the size of the domain depends on the power D of the diameter with constants, okay, for the way that this is done. And now, if you look at the error estimation that we know with respect to HT for quasi-uniform partitions, what we know is that the norm of U in general, U minus UH, and this is with the M norm, omega, is controlled by, now here we have usually written this as the sum on all elements on the triangulation, as we have HT here to the power twice, and we had here K minus M, and then we have norm U M here, and this is square to the power 1/2. Okay? And when HT can be taken out, so when you have this, which is controlled, and sorry, this is not M, this is K. When you can actually control the norm of what's written on the right, and you can actually take out HT, you can make this a global estimate. So when HT is the same for everybody, and this tells you for a global estimate that you have that the norm U minus UH M omega is controlled by HT to the power K minus M, and then here you have U norm M, the semi-norm M of U. And this is valid for M, which is smaller or equal than sorry, I'm writing too many K here. So let me say this is L, L, and let me say this is L, L, and this is M smaller or equal than K plus 1. And this was actually L smaller or equal than K plus 1, and M smaller or equal than M minus 1. Then okay. Well, in the particular cases that we are looking at, this is usually M equal 0 or 1. Okay, so we have this estimate in general. And now, if you look at this for the case for smooth functions, actually, if you try to estimate this with respect to the number of elements, this becomes something. And now I replace, instead of being ht, I use m. This is smaller or equal than m to the power minus L minus m over d. And this is the norm u L. Okay, and this gives you the power that you expect to have for smooth L. And now the question becomes that this power that I see here is valid whenever you have a smooth function, which is here. So for smooth functions globally, what you want to have is you'll have a order that converges with the optimal number of the optimal convergence comes from the fact that the solution U is as regular as U is regular. And of course, you can have this up to order k plus 1. So if we want to make this practical, let's say for example that k is equal to 1, and let's assume that U is in H2 intersected H1 0. So it's a function which is 0 on the boundary and it's H2 everywhere else. Then what you can say here is you can say that U minus UH 0, or actually, let me write this M, omega is smaller or equal than M to the power minus L minus, in this particular case, we know what L is. L is k plus 1, which is 2 minus m over d, and this is the 2 norm of the function L. Okay, and what we are actually saying is that this is perfectly fine if you have a function which is in H2, and we would like to understand what happens if the function is not in H2. So if it's less regular, can we make a grid which is locally refined and for which this rate that I see here is the same that you would have had with a smooth function? Okay, and the answer is yes, you can do that. It's possible to do that, provided that you equidistribute the error. And if you equidistribute the error, is possible to prove. Which means eta k is proportional to delta for every k. So you're saying that the estimator is equal on every k to something which is equal to delta, example. Then what you can prove is that the norm that you get here, U minus UH, M omega, is controlled by a power. This is minus 2 minus M over D, and the norm that you put here on the right is the 1 norm instead of being the L2 norm, the H2 norm. Okay. And of course, in this particular case, this no longer true that HT min is equal to max HT. But it is true that eta k is proportional to delta for every k, which implies that locally the error is constant. And you are going to refine more where the local error is larger. And the estimator that you have for the local error contains terms which have inside the F and the residual in a certain sense. So the Laplacian of u minus F, which is this term over here, and the jumps to the gradients of UH. Okay. And this only depends on F. So you only have something which depends on the exact solution, sorry, on the data that you have, which is this guy over here. So your estimator only depends on things that you can compute, which is, I lost the definition of the estimator here. It's F minus Laplacian of UH. This is the integral that you need to be able to compute correctly, and the jump of the gradients that you have over there. Having this uniform means that whenever this object over here is large, you have to make HT small, and whenever this object is large, you have to make HF small. So if you maintain this constant, you're guaranteed to have a equidistribution of the error. If you maintain the equidistribution of the error, you can obtain the same order of convergence that you would have had for the optimal error convergence, but having here just the H1 normal distribution. Okay, and this is a very big improvement. So it allows you to basically have control of your data, provided that you know how to equidistribute the terms on the right-hand side and the terms on the local things. Okay, let me stop here.